Okay, our fourth talk will be given by Professor Chih-Cheng Hsieh. Professor Chih-Cheng Hsieh is from National Tsing Hua University. He got his BS, MS, and Ph.D. degrees from National Chiao Tung University, Hsinchu, Taiwan. And then he joined the IC Design House, named the Pixart Imaging in Hsinchu as well. And then he joined the Department of Electrical Engineering, National Tsing Hua University, Hsinchu.
You can shorten it, no problem. You can shorten it.
Okay. He's serving as a fifth member of ISSCC and A-SSCC, and he's associate editor of IEEE solid-state circuits letters and then Circuits and Systems magazine. Please welcome Professor Hsieh.
Thank you. Thank you, Professor Liu, for your kind introduction. Good afternoon, everyone. Welcome to the Circuit Insight of ISSCC 2025. And I am Chih-Cheng Hsieh from National Tsing Hua University, Taiwan. Today's lecture is about introduction to CMOS image sensor. And this topic is very interesting to me. I almost worked all my entire career in this topic, and hopefully today I can give you a very easy touring to this interesting topic. And I am quite confident this lecture will be the easiest one today. So there is no complex equation, neither complex circuit. So enjoy it. Okay, there will be 4 parts, and the first part will be the overview. And then I will introduce some key terms and the parameters which will describe the performance of CMOS image sensor. And then I will introduce some mainstream CMOS image sensor pixel architectures. Finally, we will go into some circuit, including the real and the peripheral blocks. Okay, let's start with the part 1. I will start with the optical image system, and then we will do some simple comparison between CCD, which means the charge coupled device, and the modern CMOS image sensor technologies. And then I will introduce the basic architecture of CIS chips. Okay, we know that maybe we can agree that digital imager or digital photography is one of the most important inventions in modern times, especially when the camera function has been embedded to our mobile devices, including our cellular phone. I think it changed everybody's life a lot. You can do the digital photography anytime you want, including the selfie for the social media. So I think every camera needs an optical system. So we all know there will be a pointer. Can you see that? Pointer. Oh, Korean. Thank you. Okay, there will be a lens, optical lens. The purpose of the lens is to collecting the light and focus on the target, no matter it's a film or it's a digital image sensor. And in the digital image sensor, which is our target today, there will be several functions happens in this chip. The first thing is the photoelectric conversion, which is the most essential one. It will convert the photons to the electrons. After that, we will do some signal accumulation or charge accumulation to increase the gain. And some architecture will do some charge transfer. After that, we will do the signal conversion. We will convert the electron to different type of signal domain, for example, the voltage, time, current, and so on. And finally, we will do some digitization. And after digitalization, we can send out all the information in digital domain to the following processing chip and the interfacing. So basically, this is the fundamental of the optical image system. And today we will go through all these functions and to take a look what happened in this CMOS image sensor chip. Okay, this is an example and the internal structure of the pixel. So if you have a chance to check the CMOS image sensor chip under microscope, you will see a very beautiful, colorful, jewel-like pattern, just like this one. And the color comes from the color filter, and which I will explain later. And the glow on the color comes from the micro lens. So when we take a closer look into the pixel structure, at the very top, there will be a micro lens. We say it's micro lens means that it's very tiny, and usually in the order of the micrometers. The purpose of the micro lens is equal to the lens. You will do the light bending to try to do some focusing, to project all the light energy onto the surface of the photodiode. And then beneath the micro lens, there will be a color filter. And usually the color filter will be use a so-called Bayer pattern to separate the different light energy in blue, green, and the red. I think you all learn physics, you know these three colors is the fundamental combination of every color. So the purpose is that we need to divide the different color, project to the different pixel, and each pixel will take care of the different color. And after that, it will do some post-processing to recover the final required information. So you can see that in the pixel, there will be an area for photosensing and the rest for some circuit implementation. And that's what we call it as an active pixel. And that's we will cover more detail in the later slides. Here I will introduce you the two basic architecture for the illumination. We call it front side and the back side. In the early age of the CMOS image sensor, we use the FSI, front side illumination architecture, which means that the light comes from the top view or front side of the chip through the micro lens, color filter, and the metal interconnection, then go to the silicon. You can see in the light trace, you will go through many layers, which cause the degradation and the possible optical crosstalk. It will cause some optical blockage, and it will limit the chip rate angle. You mean how wide we can collect the target image. And after that, improved version of the architecture has been developed, we call the backside illumination. We flip the chip and we let all the color filter and the micro lens has been manufactured after the silicon wafer. And light will pass through these two components and direct inject into the silicon without going through all the required metal layer. By doing so, all the drawback or downside of the FSI has been improved. And so far, the high-end imager are all using the PSI architecture. For sure, this need a very specific process, and only a few manufacturers can do this kind of architecture. Okay, let's do a simple comparison between the early stage technology, CCD, and modern technology CMOS image sensor, and try to convince you why CMOS image sensor has dominated the digital imager market in the past decade or 2 decades. And CCD means a charge-coupled device. And in the early stage, the photon-generated electrons or carriers are handled and transferred through CCD device. The operation theorem depends on high voltage biasing and high electrical field to couple the charge on the different pixel. So when you want to read, for example, if you want to read out the charge on this pixel in red, you need many times of charge coupling and the transfer until it reaches the separated readout circuit and send it out. And because that requires specific operation, the CCD device cannot be manufactured in conventional CMOS process. Therefore, the required readout circuit or control timing cannot be implemented on the same chip. That causes the CCD system becomes more complex. In contrast, the CMOS image sensor implements the photodiode circuit, digitization, timing, and everything on the same chip because it is CMOS process compatible. So let's do a simple summary of these two technologies. For CCD, the main difference is the signal type or the signal domain. Basically, the CCD uses the charge as the signal output out of the pixel. But for CMOS image sensor, it will do the charge to voltage conversion in pixel. So after that, you only need to send the voltage domain output without requiring the high electrical field-based charge transfer or charge coupling operations. So that means that the CIS technology can achieve a higher real speed in lower system complexity and manufacturing cost. But it comes with some drawbacks. The first thing is the so-called field factor, which I will explain later. Field factor is that how many area is effective in pixel to collect light. Because CMOS image sensor need to implement some circuit in pixel, as we see the picture, there will be some area which is not for photosensing. So considering the efficiency, CCD will be much higher in terms of the field factor. But as I mentioned, CMOS image sensor has dominated the market because the mentioned benefit, including the high integration and the low cost, and most importantly, the achievable imaging performance has be compatible to CCD. When the CMOS image sensor has been developed maybe 20 years ago, at the very beginning, it cannot compete the performance with the CCD. So it has been defined as a low-end product. But after some technology breakthrough, there are several milestones. After that, CMOS image sensor has dominated. It proved the performance is compatible with CCD, and then with another benefit, so it becomes the dominant technology. Okay, so this is the basic architecture of the CMOS image sensor. As you can see, the pixel array basically is the largest portion of this chip because we need a high resolution imaging. And in addition to the pixel array, you still need some supporting circuit, including the addressing, because there's a red light operation. So similar to the memory, you need the X and Y addressing circuit. And then you need some pickup and the processing analog circuit, usually implemented in current domain. So what we call it a column-wise circuit. And the other one, you still need some supporting block, including the bias generation or timing generation. And for the pixel array, we will introduce some basic important pixel. And you can see that the most important thing in the pixel array is the photodiode, because it's responsible for the conversion from photon to electron. Okay, that's the basic of the small image sensor system. Then let's go to the key terms, and which means we usually need to understand what's the key parameters to describe the performance of CMOS image sensor, especially sensitivity, efficiency, and so on. Okay, we will introduce corresponding parameters in these three stages. One is the photon to electron conversion path. In these stages, we will introduce you the quantum efficiency, QE, and the field factor, FF. And after the photon to electron conversion, we generate a charge. So we take a look at the charge domain. We will introduce you the charge storage and electrical conversion related parameters, including the full well capacity and the conversion gain. And the final one is the dynamic range. It's an overall benchmarking parameters for the image system, especially for the image sensor chair. And it depends on several things, and we can check it out. Okay, we mentioned that there are several things happen in the sensor. The first thing is the photoelectric conversion. And the purpose of photoelectric conversion is to convert the photons to the free electrons. And in this stages, we need to define the key terms, which is the quantum efficiency and the field factors. And the other thing is the charge accumulation and the storage stage. In this stage, we will use a full well capacity parameter to describe the required performance. After that, we will do the charge to voltage or charge to any electrical domain conversion. In these stages, usually we will use a conversion gain to describe the efficiency. And finally, we will describe all the system, the dynamic of the whole system. And for sure, the A to D conversion are also included. Okay, let's check it out one by one in detail. The quantum efficiency, the definition of quantum efficiency is equal to the number of photon-generated carrier divided by the number of input photons. So it's quite straightforward. For example, if there is a 100 photon injected into your sensor, how many electrons has been generated? So QE is used to describe the efficiency. If you generate 50 electrons, that means you have a 50% of quantum efficiency. And what's the photoelectric effect? We all know there are some energy in light. And when the photon energy is higher than the bandgap of our semiconductor, no matter what material you are using. Different material has different bandgap. For silicon, it's around 1.12. That's on voltage. So if the energy of the eastern photon is larger than the bandgap, it will break through the covalent bonds and generate the free whole electron pair. And that's the foundation of the photoelectric effect. It's the key why we can use the semiconductor to do the light sensing. Because is the proportional behavior. So after the photoelectric effect, the information has been converted to the electrical domain, and after that, we can deal it with our circuit. So the first thing and the most important thing in sensor is the photoelectric effect. And it depends on your sensor material, your sensor architecture, and the many of the optimal tricks. So if you want to detect the different wavelengths, you need to consider the different material. For example, for silicon, it's very good for visible light, but it cannot detect the wavelengths maybe more than 1,000 millimeters. That means that it cannot detect the near infrared range. So you need a different material to do that kind of applications. The other thing is the field factor. It's also easy. It's defined by the photosensitive area divided by the pixel area. As an example here, assume the pixel size is square in white, and then we need some area to do the circuit implementation. And the rest area can do the photo sensitive. But as you can see, it's not 100%. So we define the ratio as the field factor. So if you want to increase the sensitivity, the target is you need to improve your field factor. But there will be some limitation because that you need some area for circuit implementation. But nowadays, we all know we have the technology of the 3D stacking. So this issue has been improved by using the 3D stacking architecture. You can move some part of the circuit into the different layer of chips. Okay, the third parameter here is the full well capacity. The full well capacity is to describe how many charge you can handle, which means the maximum signal level you can handle in your sensor. We know the photoelectric effect is to do the photon to electron conversion. After that conversion, you need some wire to store the electrons. And you can imagine that basically it's the capacitance. So you can imagine that the capacitance is like a well. You can use the wells to store the generated electron to do an accumulation, like integration in circuit domain knowledge. But the capacitance value is limited, and the available swing is also limited, which means the maximum charge is equal to the C multiplied by V max. That will be your full well capacity. And to visualize this concept, you can see that when your charge is full, another coming charge cannot be accumulated on the capacitance, and it will be saturated. And that there will be no more information after that. So the full well capacity definition is equal to, as I mentioned, the capacitance for sensor multiplied by the available voltage swing. The available voltage swing is defined by your circuit. So basically, you need to carefully arrange your bias point and from your very front end to all the signal paths, and you need to propagate all to interfacing each block in the correct biasing voltage to maximize the available swing at the sensor node. Okay, the other one is the conversion gain. So we we need to remind you in this equation, the full well capacity is proportional to the sensor capacitance, CPD here. But if we use a larger CPD, we can get a larger full well capacity, but it comes with a trade-off. The trade-off will be conversion gain. Okay, so what is the conversion gain? The conversion gain means the voltage change per electron. That means you need to do the voltage to, charge electron to voltage conversion, which means the Q equal to C multiplied by V. So if you want to get a very sensitive voltage domain signal, your voltage signal will be equal to Q divided by by C, right? So if your capacitance CPD is smaller, you will get a larger conversion gain. Got it? So basically, we see that the full well capacity is proportional to the capacitance. But in contrast, the Q to V conversion gain is inverse proportional to the capacitance. So if these two things happen at the same node, I mean, if the charge accumulation and the charge to voltage conversion happen at the same node, you cannot avoid this trade-off. Okay, so we will introduce you how the pixel improvement to deal with this trade-off later. Okay. Final is the dynamic range. The dynamic range from our experience, especially in circuit design, we usually to define the dynamic range as the maximum signal to noise ratio, which means the maximum signal you can handle divided by the minimum signal, which is the minimum signal usually equal to the noise floor. Here in sensor, we use a similar definition, but actually there are two dynamic range definition in CMOS image sensor. One is that, like this one. The other one is that how to handle the brightest part and the darkest part in the same image. Because we can check this transfer curve. The X is the input photon, the Y is the generated electrons. So we can see a proportional straight line as the signal, which is proportional to the input photon. We learned about the quantum efficiency, right? So if you have a 100 input photon, maybe you will generate 80 electron. That means you have 80% of quantum efficiency. So this line will be the straight line proportional to the input photons. And then let's check the noise. There are two main noises in this system. One is the real noise, contributed from the circuit. So it is independent to the input photons. Because no matter what's the illumination level, you use the same circuit to do the real. So basically, the real noise will keep constant and independent to the input photons. But the other one is the shunt noise. The shunt noise is related to the input photons, and I will explain more later in detail. But you can just get the idea that the photons is a random process. So when you receive the 100 photons, there will be not, if you check the photons number for long times, the number will not keep the constant even under constant illumination. So basically the photon number will be some fluctuation, and that will introduce some photon generated shunt noise. And basically it will be equal to the square root of your input photons. So that's why we will get another curve here. So the total noise will be the summation of the real noise and the photon noise. So for low illumination, that signal-to-noise ratio will be limited by the noise flow from real circuit. But for high illumination, the shunt noise will dominate, and the signal-to-noise ratio will be limited by the square root of the input photons. This is the basic to understand the noise in the imaging system. So if we want to check the timing range, we need to know what's the maximum output signal value, which is determined by the full well capacity, as I mentioned. And the other one, we need to know what's the minimum detectable signal value, and which is depends by the real noise flow. So how to do a good image sweeping? You need to reduce your real noise, and you try to increase your full well capacity. Yeah, that's the design challenges in this topic. Okay, let's check the noise in CMOS image sensor. We separated the noise to temporal domain and the spatial domain. This is the funny part of the image sensor, because we need to keep in mind that it's an array, and we need to take care of the uniformity of this array. Okay, so for temporal noise, as mentioned, we know there will be some photodiode generating noise, which is shunt noise under illumination. And the other one is the dark current noise, which means that when there's no photon at all, under completely dark environment, you still see some generated electron. How it comes from thermal. So, and some interface nonlinearity. So we need to take care of the dark current noise as well. And the other part is the real circuit contributed noise. And basically, you need to check all the signal paths and try to optimize which part is the dominant noise source. And I think you may know that every amplification can reduce the input refer noise from the after or the following circuit, right? So we try to implement the front stage gain and try to reduce the input refer noise from the following circuit, for example, the quantization of the ADC. And for sensor operation, there is a specific behavior. We need to do the reset. It's like the shutter. We need to do an initialization for sensor exposure. So it's used, usually we use a switch to force the specific voltage for sensor to do to implement the beginning point of the exposure. And we all learned about the circuit. We know that when you implement the switch plus the capacitor like this one, you will get the KTC noise. So this happens at the very beginning of the signal path. So this KTC noise is very important. You need to deal with this seriously. And usually in CMOS image sensor, we use some specific circuit technology to cancel it out, like correlated double sampling. And I will also introduce this later. Okay, for the spatial noise, you can see we can classify it into the array fixed pattern noise or the column fixed pattern noise. We say it is a fixed pattern noise because it is not dependent on illumination. And after manufacturing, it comes from the non-uniformity. So it's like the mismatch in circuit. It will be fixed. So that's why it's called fixed pattern noise. And there are two kinds of fixed pattern noise, array level and the color level. So you can imagine that the array level comes from the pixel, and the color level comes from the color circuit. So every time you finish the design, you do the measurement. When you see the image, you can judge the root cause from the fixed pattern behavior. It comes from, if it's an array fixed pattern noise, you can be sure that it comes from the pixel level. In contrast, if it's showing color fixed pattern, it will come from your current circuit. Why this is so important? Because usually the pixel designer and the real circuit designer are a different group. So sometimes there will be some argument why your chip is not working. So this result will give you the clear clue that if you see it's a color fixed pattern noise, you should know that's your problem, that's your circuit design issue. Okay, then we go to the part 3. I would like to introduce some mainstream CS pixel, including the passive pixel sensor and the active pixel sensor, and finally the SPAC. The passive pixel sensor, okay, let's go. The pixel sensor can be classified into active and passive, depends on the circuit in pixel. I think it's quite straightforward that the passive means there is no active circuit in pixel. The other way, the active pixel means there are some active circuit. So we can do the comparison here that you need some amplification circuit or some buffering circuit to sense the in-pixel voltage and send it out a rate using some active circuit. And when you implement this architecture, we call it active pixel. In contrast, in the early stage of the CMOS sensor, there is only one switch in pixel to do the multiplexing. So this is like a passive selection. There is no any signal amplification or signal buffering. So it will be quite simple, cost effective, but the performance is not that good. So for modern technology, almost every CMOS sensor uses the APS instead of using the PPS. And for APS, there are still two kinds of APS. One is the 3T, the other one will be the 4T. The 3T means the 3 transistors. You can see there are only 3 transistors in the pixel, in addition to the photodiode. And so the circuit is quite simple for CMOS sensor. One transistor for reset, the other one for the input device of the source follower. I believe you all learn about the source follower. It's a very basic circuit, maybe in your second year of undergraduate in microelectronics. And the other one is the switch. So you only need 3 transistors in your pixel to do the required reset operation and the buffering operation and the selection operation. This is the 3T APS. And this pixel usually comes with a simple PN junction for the photoelectric effect. The PN junction can sense the energy of the photons and generate the free electron hole pairs. So you can imagine the diode after reset is like a floating capacitance. The floating capacitance will, the voltage on the floating capacitance will start to discharge based on your illumination condition. The more illumination, it generates more electron, and the slope will become steeper. And the other way, the slope will be small under the low illumination. So after a certain time, you can read out the voltage on the capacitance or the PN junction. Then you will know that what's the illumination condition. This is the basic of the photosensing and the readout. So we can separate the operation of the 3T APS to these steps. After exposure, we need to detect the VPD, and we do the signal readout first. Then we reset the photodiode, and we readout the reset again. After that, we will do subtraction to do the effective signal range during exposure. This information will be proportional to your illumination condition, and this subtraction can be used to cancel out the mismatch of the source follower. This is the foundation of the 3D APS operation. There come some issues for 3D APS. First, it's difficult to suppress the reset-induced noise, KDC noise. The reason is that after reset, we have some KDC noise on the VPD node, and after explosion, we will read the reset noise plus the signal out in this phase. After another reset, we will read out the reset level, but the reset noise in this phase is different from the one in this phase. So we cannot cancel out the reset-induced KDC noise in 3D pixel. And the photo detection region acts like the photosensitive region and the charge to voltage conversion. As I mentioned, there will be a trade-off because for 3D APS, it happens at the same node. That is another issue for 3D APS. And the other one is there's no protective layer on the surface. So there comes some non-ideal interface state, which will cause dark current, and there will be some coupling issue. And all these issues has been solved using the advanced and improved pixel architecture, which is the 4T APS. The 4T APS uses 4 transistors here. It has another additional transistor for charge transfer. You can see the diode structure is also different. This is the key. It implements one more layer on the surface to protect the surface interface state, to protect the coupling, and more importantly, it creates some behavior called ping. Ping means that when we do reset, all the depletion region will be increased and touched together on the N- region to clear all the charge inside this node, to do the charge transfer to here. Actually, this architecture comes from the CCD. That's why the performance of CMOS image sensor can be compatible with the CCD. It all comes from the adoption of this pin photodiode. Okay, I need to speed up, right? Okay, and so let's see the operation. Again, after exposure, we reset the VFD first. Then we read the reset level first, including the KDC noise. After that, we turn on this transfer gate. The accumulated charge on photodiode will be transferred to node VPD, and then we read out. So in this readout, we read the store signal and the KDC noise as well. So the KDC noise in phase 3 is identical to the KDC noise in phase 4. So after subtraction, we can cancel it out completely. That's a big jump, big performance improvement by using the 4T APS. But there comes some issue. It's difficult to manufacture precise control architecture of the pin diode. That will need some experience. Okay, due to the time limitation, maybe I skip the spec. This is another advanced technology for the depth sensing. Okay, let's go to the final part. This part, I just introduced the required real and the peripheral circuit for each CMOS image sensor, including the pixel the architecture and the timing and the peripheral. This is the architecture. Usually, we can choose to do the serial real, parallel real, or current parallel real, or the pixel parallel real. So you can see that it all depends on the required circuit complexity and the throughput. When you need a very high throughput, you need to increase the parallel processing capability. You will go through the more parallel architecture. And for the simple and the slow implementation, you can use the serial readout. Okay. And current parallel readout will be is the most popular one so far in the commercial product, because it provides the best balance between the throughput and the cost. And for sure, there's some mismatch you need to deal with, but through some calibration and through some circuit techniques, you can deal with the current-to-current mismatch. So far, current parallel architecture is the mainstream in the market. And the pixel parallel real can provide a high throughput for some advanced application. For example, you need some intelligent imaging. You need to implement the pre-processing task under the sensor array directory. Take the advantage of the 3D stacking technology. That this will be the new trend for the future sensor development. Okay. And the timing. Timing is important in the sense that you need to understand that it's digital photography, so we need to do the exposure and we need to do the readout. So let's check the shutter operation. In sensor, there are two shutter operations. We know that in the conventional camera, we use a mechanical shutter, but for CMOS image sensor, we need to implement the electrical shutter. There are two kinds of shutter has been used. One is the rolling shutter, which means that each row in this pixel array will be reset, exposure, and the real sequentially. That means the starting point of each row is different compared to the global shutter. We will control the shutter simultaneously for each pixel to let them, the starting time and the ending time of the exposure will be the same. What's the difference? For using by using the rolling shutter, you will see there comes some well-known artifact, because when you capture a moving object in a high speed, the different row, the exposure starting time of different row will be different. That means that your triangle will be tilted after the rolling shutter operation. And this issue will be solved by using the global shutter. But global shutter comes with another issue, which is the charge storage capacity. Because after the shutter, you need to read it out row by row. So different row, you need a different holding time. So you need a very perfect capacitance or perfect optical blockage to avoid the optical leakage or the electrical leakage. Okay, peripheral circuit includes the source follower, CS, PGA, and ADC. Source follower is a simple circuit for signal buffering. CDS is for the double sampling and the subtraction, as I mentioned. So after the source follower, you need a circuit to do the subtraction. Maybe switch cap based circuit is a good candidate. And the PGA is for the signal amplification. You can implement in share architecture or in the current share architecture. As mentioned, switch cap using OPAM is a good candidate for the signal amplification. Finally, this is the ADC. Thanks to Professor Harper's introduction, you all know the different ADC is suitable for different applications, depends on required throughput and the power. And then in CMOS image sensor, there's another issue you need to take care of, is the area. You need to take care of you need to concern the area requirement for your ADC. For example, for the pixel parallel ADC, is not possible to implement the very complex circuits. You need to do some share arrangement. Okay, sorry for the hurry. So finally, I will summarize my talk. I introduced the CMOS image sensor from photons capturing, storage, conversion, and then digitization. And also introduced some performance metrics like QE, FF, and DR. And we explored some pixel architecture like 3D and 4D. And finally, I would like to encourage you, this topic is still growing with many advanced applications, like smart imaging with embedded AI, or large format high-performance image for motion capturing, or even the biomedical sensing for next talk. Okay, so that concludes my talk. Thanks for your listening.
Okay, so if you have a question, I think we can take just one quick question. Okay, please.
I have a small question.
Yeah.
First, thank you for the speech. Maybe I know about the DVS. Do you know DVS?
Yeah.
The dynamic vision
Yeah.
sensor. Yeah. So maybe I know about the DVS is its capability of low latency and highly dynamic sensing. So how do you think of DVS and
Okay, good question.
it has a promising future?
Okay. Okay, I didn't cover the details in this talk because it's not a basic architecture for CMOS image sensor. It's specific for the motion detection. The full name of DVS is dynamic vision sensing. The whole mechanism is different from what I introduced today. Basically, it uses an in-pixel event detection circuit. And the most importantly, I introduced all the sensors need a charge accumulation phase, right? But for DVS, it's a real-time sensing. It's not, there's no accumulation at all. Yeah, so it uses like a logarithmic sensor to convert the photon to current and then to voltage directly, continuously. Yeah, so yeah, DVS has been, I think it has been reported maybe more than 15 years, and and it has some successful demonstration in applications of motion detection. But the drawback of DVS is that it is not nothing like the conventional image sensor, so you need to define a new interface, including the data format. So the existing signal processing system cannot deal with the output of DVS directly. You need some transformation to utilize the existing signal processing engine. So that will be a big problem so far. And the other thing is there's no accumulation. That means there's no in-pixel gap. So the sensitivity is quite poor in DBS. So that causes a lot of false alarm. Yeah, I mean, because it uses the event to do the motion detection, but because of the noise, the poor signal to noise ratio, it will cause a lot of the false alarm issue in this field. Okay, maybe we can discuss more later. Okay. Thanks for your question.
Thank you. Yeah, please thank Professor Chen for his kind.
Thank you.